Hi there, my name is Raymond Doe, and welcome to my Physics 2212 Lab 4 video on circuits. Hope you enjoy. The purpose of this lab is to use the principles of energy conservation and current conservation to accomplish three things: to predict the behavior of circuits containing resistors in series and parallel, to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. To not only complete this lab, but to also comprehend the conceptual nature of circuits and currents, we will need to first understand and utilize the fundamental physics concepts of Kirchhoff's loop rule, current conservation, the behavior of steady-state circuits, and Ohm's law in all of its various forms. You may take a few seconds here to pause the video to see a preview of our results, which I will be explaining throughout the process of the experiment. In part 1 of our procedure, we are given the circuit model below and first asked to calculate the currents of I1 and I2. Before that, however, we must establish our system, surroundings, and initial conditions. The system is our circuit with the surroundings as the environment external to that circuit. For our initial conditions, we know that we have two batteries holding 1.5 volts each, a resistor of 47 ohms, and another of 100 ohms. And since the circuit is in series, we can deduce that the I1 is equivalent to I2. Our general assumptions for this lab is that the resistance of the wires and ammeter are negligible. This is our equation for this circuit, accounting for all elements involved. Since this is a closed circuit, we can use the loop rule to know that all potentials sum to zero, and with this, we can algebraically manipulate this equation to solve for our currents I1 and I2, with the results being 0.02 amperes. The graph displayed on this slide illustrates the flow of current through our circuit by segments A through H. This graph makes sense, as from A to B, the voltage increases to 3 to sum both 1.5 volt batteries. Segments C through D and E through F decrease in current, as those regions contain resistors that diminish the current. And all segments in which there is only wire experiences no change in current, as shown by the plateau regions on the graph. We are also asked why the ammeter reading did not change during this experiment. Well, this is because due to high ohmic resistance, there is little current flowing through the circuit for the ammeter to read. This slide simply shows my simulated circuit as well as my calculations for resistance of all elements involved. Notice how the resistance of the wire and ammeter are zero in this case, as we assume their resistance to be negligible for the means of this model. Now in part 2 of our lab experiment, we are first instructed to simulate and observe the effect of capacitors on the ability of current to ignite a light bulb. The light bulb initially shines brightly, but gradually decreases in intensity. This occurs as the capacitor charges. The overall current decreases to zero by taking the electricity from reaching the bulb. When the battery is removed from the circuit, there is nothing to maintain the potential difference between the plates, and the capacitor will discharge. As this happens, there will once again be a non-zero current flowing through the circuit, and the bulb will light up. These are the main results of our experiment. Using the timer, I recorded the voltages of my current at various seconds, and using this natural log equation, I was able to generate a line graph in Excel with this specific slope equation: y equals negative 0.1511x minus 0.0522. Then, using this slope, I was able to calculate the length of time it took for the capacitor to discharge, with that being 6.62 seconds, only 0.62 seconds off from the true discharge time of 6 seconds as shown below. We are now posed with two what-if scenarios. When asked, what if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and what would have affected the circuits we hooked it up to? Well, in real life, we are unable to observe the assumptions we made in our virtual model that the ammeter's resistance was negligible. This means that if we were able to run this experiment physically, we would see a decrease in our predicted current due to the ammeter's actual resistance being greater than zero and breaking down the current. Then we are asked, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? In this case, it would be reasonable to assume that the capacitor would become fully charged immediately due to the absence of resistors. However, not even this prediction would be completely accurate if applied to reality, because wires and batteries have their own resistance that will prevent immediate charging of the capacitor. Possible sources of error that could have compromised the integrity of my results include a mistake in the recording timer, slight miscalculations in precise values, and incorrect ammeter readings during simulations. Thank you so much for your time, and I hope you've enjoyed.